Let's see. Okay. Right. So now to eliminate A dot, you have to assume that reaction 1 is in equilibrium and that K1 so that means K1 equal K1 and K minus 1 are much more than K2. So that's what the rate limiting step means, and that's what the equilibrium means. So you could say that the equilibrium of reaction 1 okay. So there we go. So your minus RA is K2 times K times A. Does that work?
I have a question. So I don't understand why a steady state approximation isn't allowed here. Like I understand how rate limiting step simplifies it.
Yeah.
Right, but doing a steady state approximation would also give you an equivalent answer.
It would give you one. It would give you an answer.
That's like correct though.
It's not incorrect, because here's what's going to happen. The next part of the class is going to be how do we test which one of these answers is correct. Right. So as I mentioned in the beginning, so now we are saying that, okay, if you're told, in this case, you're told that reaction 2 is rate limiting. So what that implies is that the rate basically depends on it. Nothing else. It doesn't depend on anything else. So that's what it means.
I understand that, but I guess I'm a little confused because I guess like in office hours yesterday, I was asking, hey, we did out problem 4 in the homework the long way with the steady state approximation, and you said that that the two answers are equivalent and you can get from one to the other. And so
yes,
I don't understand why like C is a problem to put in this situation, because the math using the steady state approximation gets you there.
I see what you're saying. Okay, that's
right. So like it's
frustrating. You're not wrong. I think that yeah, in principle you should be able to go from C to B.
So if you can go from C to B and
you should be able to go from C to B, and I think I know what you mean. So that's my mistake.
So shouldn't they both? Why? I guess what I'm asking is, why would C be marked wrong if you can go from C to B if you give equivalent answers? Right? Like in principle, C is correct. Like I understand it's not the most simplified form that you were targeting, but if we give you a correct answer, is it not still correct?
I can see your negotiating skills, but I'll counter with this. I will still take into account what has happened here and make sure I make up the points for it. But I will say this: if you have B and C are not actually equivalent.
Right, B is a simplification of C. I understand that.
I wouldn't even call it a simplification of C. And maybe I misspoke when I was talking about this before. I wouldn't call it a simplification of C. I think that's a misnomer.
I mean, when I say simplification, I mean in the sense of you're using an assumption to simplify the equation. I'm not saying like you can rearrange C to get B. I'm saying like
yeah, exactly. So yeah, so it's not in that way. No, I see what you mean. So if some of you used an SSA to get answer C, and I believe I'm in this particular case I am leaning towards giving full credit for it, because I didn't ask you to actually use the rate limiting step. I just said if the second step is found to be rate limiting. and that was insinuating that one should use the rate limiting step approximation, right? That's sort of how the question is formulated. I think that's misleading. If I had told you to use the rate limiting step to do this, then the approach of C would be wrong. Does that make sense?
Right. No,
Yeah,
I
yeah.
agree with
Okay.
that. So
Got it.
I mean, the way I approached it, I saw the question and I said, okay, I'm not confident in my rate limiting step skills because I've only, gone through it maybe once. So I just used the steady state approximation thinking, that would still get me to the right answer.
No,
Since my hands weren't tied, I used
got you.
both of them.
Oh, I understand. I know what you mean. Well, in any case, you went through the harder, the longer, the
It
longer
didn't take that
process.
long, it wasn't too bad, It was
Okay,
just,
no, I got you. I see what you mean. So anyone who's put C now, the only downside to this is that if someone just guessed C, they also get the right. They also get full credit.
well, you can
So,
say the same thing about people that guess B,
yeah, I know.
it
I
goes
know.
both ways,
It
right?
goes both ways. All right, I got you.
Thank you very much.
Yeah, no problem. Thanks for bringing that up. I think if I should have explicitly said use the rate limiting step. I think I was just trying to be clever, and that backfired. The For question one, I think someone said let's go over that. So this is just looking at the rate expression. So if you fix concentration of nitrous oxide and you're looking at the graph. The graph is looking at concentration of carbon monoxide. So at very low carbon monoxide concentration, it's very clear that you can eliminate the carbon monoxide from the denominator. So that means this is gonna go as first order in carbon monoxide. So it's gonna go as a straight line. So you see, it's gonna basically, if you eliminate nitrous oxide, now if you eliminate this term, because this term is much smaller than this one, so with respect to carbon monoxide, it goes straight up. So that's what this curve is looking at. Now you get to a point where you have a lot more carbon monoxide. So now that term becomes bigger than nitrous oxide, so it becomes negative order. So it goes down. So that's why this is correct. This is just looking at essentially pretty strange. Yeah, I just wanted you to kind of look at this and realize that how the denominator is changing with increasing concentration of carbon monoxide. Okay, so with that, okay, so where are we? Oh yeah, we've been recording, that's good. Okay. We're not gonna be able to do everything we plan to do today, but that's all right, because there's a lot going on. The one thing we'll do, however, is for this class, unfortunately, we're going to skip bioreactors, and for two reasons. First reason is time. Second reason is that the nomenclature for bioreactors is a departure from what we've been using. So it doesn't really help in this respect either, because we are going to introduce yields and titer and those types of things that are kind of a departure. Now, if we have some time at the end of the course, which I doubt, but I'll say that, we may just sort of touch base on it just so you can see it. But it doesn't really add anything to the fundamentals we're learning, because there are courses in biochemical engineering that are essentially devoted to cell growth and biochemical reactions. So that would be a better or more complete picture, because this way I wouldn't want to do a very half-baked job. Now, one thing that has happened in this course compared to last semester is that in this time around, we're introducing surface reactions and pressure drops. So it looks like it was too ambitious to try and to add 3 new things in the course instead of 2. So that's the status of things. So what are we gonna do today? So today we're going to finish up the interpretation of the Michaelis-Menten, or at least enzyme mechanism, and simplify this to a Michaelis-Menten approach and show and talk about what Michaelis-Menten is. And then the next, and that'll take probably 25 minutes or so. And then we will talk about the different types of inhibition in enzyme catalysis. Then after that, we will talk about different steps in catalytic reactions. We'll start that today, and we'll finish that up next class. And then next class, we'll also start talking about the next part of this second half, the middle half of the class, the middle part of the class, which is how do we check the validity of a rate expression using derived experimental data. And that will make the bulk of the exam too. So that is, so essentially exam 2 is going to be pressure drop, recycle reactors, reaction mechanism, and correlation of data to fit a rate expression. So there's essentially 4 topics, which could result in 3.5 to 4 problems. Okay, let's begin. So like I said last time, we actually introduced 2 methods to derive a rate expression given a mechanism, which is a sequence of elementary steps. And those 2 methods are the steady state approximation and the rate limiting step methods. So what was nice here is that we introduced these methods without talking much about the nature of the reactions themselves. We just introduced them based on algebra. We didn't talk about the nature of the reaction. So today we'll do a little bit of talking about the nature of the reactions and how they and what makes these reaction rate expression arise. Okay, so first we'll finish up our enzymatic reaction approach. So we talked about the way we actually, to derive the RLS, well, we use the RLS, I would say. So we did it in enzyme catalysis, where we had the substrate plus enzyme that binds and forms an enzyme substrate complex. This enzyme substrate complex then reacts in the second step to have an enzyme product complex. And we stated that this is rate limiting, and this is often the case, that the actual transformation is rate limiting. And the third step, which goes from, is essentially releasing product from the active site of the enzyme and regenerating the enzyme to go another cycle. And what we had shown, at least using these arrow representation, is that if the second step is rate limiting, the first steps, so this is reaction 1 forward and reverse, and the third steps, reaction 3 forward and reverse, are much faster than the second step. So we had gotten to that point. And by doing a bit of math using the rate limiting step approach, what the rate limiting step stipulates is if the rate limiting step is the actual reaction rate, the others are in equilibrium, or the others are as fast as the rate limiting step. They couldn't be faster. They couldn't be slower. Right. So that's what we have said. So we have gotten to this form of the rate expression after some rearrangement. And this is in the book. We've gotten to this. this form. In this particular form, Kc equilibrium is actually equal to K minus 2 over K2 times K1 times K3 prime. And that's 1 over K1, K2, K3 prime. So that's 1 over equilibrium. And this is from thermodynamics, saying that if you have, so from thermal, one thing we sort of postulate, and that's just a small little, that's just a small little review, is that if you have 3 concentrations, say like this, if you have this, it's actually equal to themselves in equilibrium with their equilibrium constant in other reactions. Oh, sorry, this is Kc. So this is something we picked up from thermal, and this is something that will come in handy by the end of the lecture or by next lecture as well. But I wanted to postulate that you don't have to think about it too hard now, but in the next lecture we'll talk about it again, and that will be a bit clearer when we use it again. So we get to this form, and this looks pretty complicated. The first thing we realize is that this 1 minus this term here, it represents how far from equilibrium is the reaction. Is the enzymatic reaction. So, you know, if the reaction is far to the right, that term on P product divided by substrate divided by equilibrium constant is going to be close to 0, which is often the case in most in many enzymatic reactions. But otherwise, you know, the reaction itself is reversible. But this is a term that tells you how far from equilibrium you are, especially this this right side here. Yeah. And the other, see, now I wanted to clarify something. So K1 here is the equilibrium constant for the formation of the enzyme substrate complex. UK3 prime is the equilibrium constant for the decomposition of the enzyme product complex. That the reason why we kept calling it K3 prime is because often the convention is to have equilibrium of formation instead of equilibrium of decomposition. So that's why we kept calling it K3 prime. But what we can do is say that essentially K3 is 1 over K3 prime. So we can replace K3 prime with K3 in the reaction, and we'll just end up with this form where Rs is K2, K1, P, and then we have the distance from equilibrium term. So if we take this form and then we start thinking, how do we simplify it? So we're going to start simplifying this form to get to something that we often use, which is that we most often use. So that's what we're going to do. So if we suppose that the dissociation of the enzyme product complex is irreversible, and that suppose that is the case, that this is irreversible. So what this means is that K3 prime is infinity, goes to infinity, and which also means that yes, I can do that. Which also means that this equilibrium constant with KCEQ is also going to infinity. So that means that the right side term here drops out. So the right side term drops out. So that simplifies things considerably. And the other thing that drops out is the third term of the denominator. So what drops out are this term and this term. But the one thing to keep in mind is that this term dropping out is a term that also refers to product inhibition. Essentially, what you can realize, what you can see from this equation is that if the product concentration is high, the rate will be lower. So product inhibition is often a phenomenon in enzymatic reactions. So even if the reaction is irreversible, you can have product inhibition. And we'll actually talk about that in a minute. But we'll get back to that in a minute when we analyze this even further. When we look at the types of inhibition that can occur with enzyme catalyzed reactions, we will look at that. So yeah, now we're going to get to the exciting part where, because we can remove these terms, we're left with this. And if we divide by K1, large K1, if we divide by that, then we are left with this form. 1 over K1 is often called Km. Now remember that K1 is small k1 over k minus 1. And that is the equilibrium of formation of the enzyme substrate complex. So Km is often called the affinity. It's the affinity of the enzyme for its substrate. So that's often what it's called. So that's what Km is often called. And K2. So now we're looking at some biochemistry. So we go from our chemical engineering to we're transferring to some biochemistry terms. So K2 is actually called Kcat, and that's called the turnover number. The turnover number is in inverse time. So what it is how many molecules the enzyme turns over per time. So that is a turnover number. So you can see from the numerator, if you look at the units, so if you have K2 is inverse time, enzyme concentration is in mole per, let's say mole per liter. Substrate concentration is in mole per liter. Substrate concentration in the denominator is also in mole per liter. So that means Km has to be in mole per liter. So that the rate is in mole per liter per time. So you can see from the units that this is consistent. And talking about and the reason why this works is because if you remember, let me think here if this works out. Will it work out? Yeah, so what we can do, yeah, we can also see that it works out if we look at the units of K1 and K-1. That should also work out. That should be only in concentration when you look at them for K1, or at least inverse concentration. So now you can finally write the rate of consumption of the substrate is Kcat E naught S over Km plus S. And this is the Michaelis-Menten equation. So yeah, this equation is very famous in biochemistry. This is what often one uses to calculate the kinetic constant of enzymes. So the two kinetic constants of enzymes are going to be Kcat and Km. So where the Kcat is the turnover number, and the Km is an affinity of the enzyme for its substrate, and the Km physically represent the concentration at which half of the maximum velocity is achieved. So what does that actually mean? So what you can often see written is this form where people lump together the enzyme concentration and the Kcat to give you a Vmax. So the Vmax is maximum velocity. So the Km is a concentration at which half of that maximum velocity is reached. That's what this means. Now, once again, you can look at certain what do you call it? Manipulation. So if you have high substrate, at high substrate concentration, the maximum rate is actually about equal to Vmax. So if you have an enzyme and you want to know the fastest it can go, if you don't have substrate inhibition, because you can also have substrate inhibition, you will see that the maximum rate is equal to Vmax. So you can determine this experimentally by increasing your concentration of substrate. And I can graph this for you. So this is substrate concentration, and this is the rate. It looks like this. So if you reach a certain concentration of your substrate, you will have reached Vmax. Now the Km is a concentration at which half of that is reached. Half of that maximum velocity is reached. And lastly, if you have low substrate concentration, So the Km, so that means Km is much, much higher than S. And in this case here, it means Km is less than substrate concentration. If you do that, you can determine it is first order with substrate, where the slope is Vmax over Km, and it's linear in the region of very small substrate concentration. So yeah, so this is the manipulation of Michaelis-Menten equation. And in your homework, at least your homework will ask you to fit, and we'll go through these fitting experiments next class as well. We'll ask you to fit data to, let's say, a Michaelis-Menten curve to determine constants such as Vmax and Km. And there are many ways to do that. One ways to do that is called the Lineweaver-Burk plot. Where if you take the inverse, so if you do of the reaction, if you take the inverse, you'll have this form. So you can plot this form, and it should be a line where the slope is Km over Vmax and the intercept is 1 over Vmax. So the Lineweaver-Burk plot is something that we're going to talk about next class or in two lectures, how to fit data to a Michaelis-Menten plot. But we'll get back to that. Now, before we move on, we wanted to talk about some types of inhibition. Now we're going to do this. Let me see here. Yeah, we're going to talk about inhibition of enzymes. And the nice thing here is that everything you've learned so far allows you to look at different types of enzyme inhibition. So that makes things a little bit more accessible. So one type of inhibition is called competitive inhibition. The final forms of these equations are in almost every biochem book, but in this class here, we actually understand how they come to be. So we are actually deriving them, which is really nice. So a competitive inhibitor is an inhibitor that binds in the active site of the enzyme and blocks the substrate from coming in. So you can form your enzyme substrate complex, and you can go through the process where you can, I'm simplifying here a little bit, where you can go. So I lumped two steps, enzyme substrate to enzyme product and product release. So I lumped these two into one step to make it simpler, because this is still rate limiting in this case, right? This is still rate limiting. And then we have this particular interaction which inactivates your enzyme. So this is an inhibitor I that binds to the active site and inhibits your enzyme. Now we're gonna derive the expression for one such type of inhibition. Okay, so we're gonna do it. Okay, yeah, we're gonna derive that. I got slightly confused with my notes for a second. So if we say this is the rate limiting step, because it often would be, the substrate depletion expression is just K2 times ES. And we can then look at, so this is, we first express our rate in terms of the rate limiting, step. Second, we're going to use equilibrium relationships. Oh no, can't write relationships. I'm going to use equilibrium relationships to remove active centers. So that's what we're going to do. So we can look at the first reaction where K1, large K1, is ES divided by E times S. And we've done this before. So we can calculate ES is equal to E times S times K1. So we've calculated this before. The unfortunate thing is we don't know the free enzyme concentration. So for that reason, we often do we do a side balance. So that's the third step in this case. We do a side balance. And the side balance is important when you're dealing with catalyst and enzyme. So if you have reactive intermediates, you may not have to do a side balance. So if you do a side balance, so your total enzyme concentration is now equal to your free enzyme plus enzyme bound to substrate plus enzyme bound to inhibitor. So, because we have that as one of the steps. So to eliminate, to put everything in terms of free enzyme, right? We're gonna end up putting everything in terms of free enzyme. So we can now take a look at the K3, which is now equal to concentration of enzyme inhibitor complex divided by concentration of enzyme inhibitor. So we can calculate EI as this. So we can now plug everything in to find out that the free enzyme is equal to this. Okay, so free enzyme is equal to this. So now we can combine everything in our first equation. So we can combine 2 and 3 in 1. If we do all this combination, oh, that's not working. We find this form. Okay, so once again, if we divide by K1, so we're going to try and make it in terms of our Michaelis-Menten form. So if you divide everything by K1, so it's now K2 E naught S divided by 1 over K1, that's Km, plus S plus K3 over K1. Actually, before we do that, let's do this better. Let's keep it as 1 over K1 and K3 over K1 times I. So we can put the top as Vmax just to make it simple. And the denominator now, if you factor 1 over K1, 1 plus K3I right? So 1 plus K3I plus S. We're gonna do 2 more small changes. So if we talked about how K3 is the rate of formation of the enzyme inhibitor complex, so we can change that to the rate of dissociation of the enzyme inhibitor complex, which is often what is reported. So it's a choice so much as it's easier to calculate the dissociation of the enzyme inhibitor complex than the other way around. So that gives you Km 1 plus K 1 plus I over Ki, so that's K, where Ki is 1 over K3. Okay, so that's pretty much what we're looking at, plus substrate. So basically, you can see how we essentially derived a competitive inhibitor. So this is an inhibitor that binds directly in the enzyme active site. Now, one thing you can notice is because the inhibitor binds in the enzyme active site, what the inhibitor does, it changes Km. Because it binds in the active site, it's going to change the affinity of the enzyme for its inhibitor. So that's pretty interesting. Now, yeah, so it's going to change this particular term of the equation. And then when we go back to fitting, when we look at how things fit, if you were to plot a Lineweaver-Burke plot by inverting the rate and then manipulating these certain things, you would find that if you were to do, this is minus 1 over, this is 1 over S. It's not the way I wanted to write it. So if you do this, so without inhibitor, your curve is gonna look like the straight line. But with inhibitor, what's going to happen is the Km is going to change, meaning that your curve is gonna look like this actually. So this is with a competitive inhibitor. And this is without inhibition. What's happening? I can't write inhibition, so. So these are some of the representation of kind of enzyme inhibition. Now you should get ready because on your exam, I'm gonna ask you to derive this one. You should just know that because that's what's going to happen. And I'm not changing my mind about it. So you already have something to look forward to. So, and in your homework, you're gonna have to derive another one. So there are 3 types of inhibition. You have a competitive inhibitor. You have an uncompetitive inhibitor. This is the second type of inhibition. In an uncompetitive inhibitor, the inhibitor does not bind to the enzyme. It binds to the so Vmax. What does Vmax mean? Vmax, sorry, I left this one behind. Oh my goodness, that was a long time ago. So yeah, so Vmax means the maximum rate of the reaction. This is how fast the reaction can ever go. So I think I have a plot here. So right there, if you plot your Michaelis-Menten curve, is going to plateau because of the form of the reaction. It's going to plateau essentially at very high concentrations. basically it's just going to reach a constant, because at very high concentrations, the substrates are going to, in the numerator and denominator, are going to cancel out. So you're going to end up with a constant, which is going to be Vmax. So that's what Vmax is that the fastest the reaction can go. Okay, sorry, I skipped that, and I don't know if I had explained it before. So we can look at the form of inhibition called uncompetitive inhibition. What it is that you still have your, we'll put the K1s and K minus 1s here. What happens is you still have your normal reaction. For simplicity, we'll say that K2 is rate limiting. The second reaction is rate limiting, and the enzyme and we combine it with the formation of enzyme product complex, just to keep things simpler. And what actually happens is that the inhibitor I binds not to the enzyme, but to the enzyme substrate complex reversibly, to gives you an IES. If you go through the same process, right? You set up your rate limiting step as the second step. You put in, equilibrium to calculate the remaining steps. So you do the same thing, and if you do this, you'd find that Rx is Vmax X over Km plus S times 1 plus I over Ki. So you can see that an uncompetitive inhibitor does not mess with the affinity of the enzyme for its substrate. It messes with the slope of the, not the y-intercept, sorry. It messes with the y-intercept of the Lineweaver-Burke plot. So if you plot this, your uncompetitive inhibitor is going to do, so this is no inhibition, and this is gonna be uncompetitive inhibitor. So it's always nice to see how the reactions, the equations themselves, explain the phenomenon. So on your homework or exam, because there's one last type of inhibition, the question is derive this. Now, I would not be too concerned because I'm sure one could Google that and find the derivation. But the key here is the ability to understand why this happens and to relate on competitive inhibitor the way it plots, at least in your Lineweaver-Burke plot, by taking the inverse at both sides and see that the y-intercept is what's being changed and not the slope. The slope remains the same. Now, a third type of inhibition, now I'm going through this quickly, but otherwise it would be to derive these forms, but it's the same process. The third type of inhibition is called non-competitive. To be honest, I never quite understand why it is called non-competitive. It's a strange way to say it. So the mechanism for that is a bit more involved. So you have K1, K minus 1. You have your reaction as normal. Once again, I lumped in the enzyme substrate to product and the product, and the product release steps. So I combine these steps. Now this is small k, by the way. So here's what happens. The inhibitor binds every form that is present. So the inhibitor binds the enzyme, free enzyme. The inhibitor binds enzyme substrate complex. And the inhibitor binds and the enzyme, and the enzyme inhibitor complex binds the substrate as well. So the enzyme inhibitor complex also binds the substrate. So people often refer to this as mixed inhibition. So all these are inactive. People refer to this non-competitive often as mixed inhibition because it has both competitive and uncompetitive inhibition. And the math to do this is a bit more involved because of all the forms of the total enzyme. So if you have your total enzyme concentration is going to be the addition of all of these. So if you go through this, you find that the final form is times 1 plus I over ki. Now, once again, you can tell that because it's mixed inhibition, if you were to do once again your inverse plots, your Lineweaver-Burke plots, no inhibition looks like that, but your non-competitive inhibition is going to change both the slope and the intercept. So this is going to be non-competitive. And this is no inhibition. So now what are we going to do with this date, with this? In the next part of the course, in about next class or 2 classes from now, 2 lectures from now, you could be given data and be asked to determine based on the data to plot this. In this case, it would be plotted, for example, using this to determine these kinds of things. So you'd have your slope would be determined, and your slope would be equal to, depending on what type of inhibition or if there is no inhibition, and your intercept would be, a certain value. So from these values, you'd be able to determine your Km, your Kcat, and your Ki. So that's just feeding data. So it's the linear feeding of data is pretty straightforward. I think many of you have done this many times before, feeding data to a line. The is to know what to plot against what to get a straight line. But these particular forms of the inhibition sort of tells you what to plot against what often with the Lineweaver-Burke plots. The last type of inhibition is substrate inhibition. We've already sort of touched on product inhibition. In the general form of the equation. So substrate inhibition. So the only difference is rather than having the inhibitor binding the enzyme substrate complex reversibly to give this, what actually happens is substrates bind the enzyme substrate complex to give an SES, and this is also inactive. So from there, what you can guess, what you can imagine what happens is that in your competitive, or at least in your is it in your uncompetitive inhibitor plot or equation, sorry, you will basically end up replacing the inhibitor concentration with substrate concentration. So you would end up with this form. Now the Ki, it doesn't refer to inhibitor. It refers to substrate inhibition instead of an inhibition. Equilibrium constant rather than the but rather than inhibitor equilibrium constant. So that's the difference there. So here what you can kind of see is that at high concentration of substrate, the equation actually looks like this. So because at high concentration of substrate is essentially saying that S is much higher than Km. So you get essentially, and of course S squared is much higher than S, much higher than Km. So you get this form. Oh, there is an S here. Forgot that. Yeah, so you get this form of the equation. And then if you have low substrate concentration, you get what you had before, which is Vmax times S over Km. So if you were to plot this normally, not Lineweaver-Burke, just normal plot, concentration versus minus RS. So the concentration would go up, plateau somewhere, and then go down. And that would be an S max. And here would have a Vmax. I guess it would be an R max. Right, so we don't know if it's actually Vmax. It's not, it's Vmax over Km times S, so it's an R max. It just reaches a plateau and then comes down. Okay. So these are, in general, some of the inhibition types. So the one thing to keep in mind is the ability to derive either the, well, yeah, you can actually think about deriving this, but it's actually very similar to the uncompetitive inhibitor. So that's very similar. You can think of deriving this as well. So either on your homework or the exam, you'll be asked to derive one of those three, either this guy, or the last one. And if you follow your rate limiting step and the approach of equilibrium of the other steps that are not rate limiting, that should be a piece of cake. Just keep track of your variables. Essentially, that's the harder part of this approach. Okay, are there any questions? Because we're gonna take a short break, and then when we get back, we're gonna talk about something that should, I think, excite you even more, because we're gonna look again at heterogeneous catalysis. And the nice thing about it is, again, there's nothing particularly new, right? It is just looking at our rate limiting step approach and applying it to things that are more, that we related to the steps of catalytic reactions. So that's what we're actually gonna do. So the rate limiting step approach is the same. And that's what I liked that we covered it as just algebra in the class before. So the rate limiting step is the same. So now we're gonna just apply it to, say, a reaction where the surface reaction is limiting, or the absorption step is limiting, or the desorption step is limiting. But it's the same idea that we go. We just we're going to end up introducing a few new terms like the Langmuir isotherm or the Ely-Rideal equation, these types of things, but it's the same idea. Nothing to worry about. And in doing so, if I were to say, in doing so, it allows us to speak more as kineticists. It allows us to speak as chemical engineer and chemical kineticist better when we introduce it in terms of these heterogeneous catalysis sort of approaches. Okay, let's take a short break for 5 minutes or so. Then we'll come back and then continue. But feel free to ask questions if you have any right now. Okay. So, and we've looked at basically how we can derive what is partly, not every form of the inhibition of enzymes, but we looked at least how we can derive, let's say, competitive inhibitors that inhibit enzymes. And, keeping that sort of stored in your brain, next lecture and the lecture after, we'll start looking at how do we determine this constant based on data, and how do we fit this data using either linear regression or by doing linearizing rate expressions. So these are two different ways that we're going to look at how to test experimental data against the rate expression. Now, before we do that, this last little bit here is one that will interest lots of you, let's say, who wants to do catalysis as a grad student, or if you want to work in industry and you talk about using catalyst, because about 80% or so of all the chemically catalyzed reaction industrially happen on a heterogeneous catalyst. So, in some ways, it's important to know this information. Now, this information, when we look at it more in depth, is very, very complicated. However, in this part of the class, we will just simplify some of those steps in catalytic reactions. Now, one thing I want to mention before I move on, as you can see, the substrate inhibition section do not feature in Roberts. They actually come partly from Fogler and a book by Mark Davis. And you can go on the Fogler website, I believe it's chapter 9 or 10. It's chapter 9 or 10. So you'll find it pretty easily. And then they have a few explanations of all of these terms. I find it necessary to talk about that because biology and biochemistry, biochemical engineering has become a very large part of chemical engineering because there is a big push to do green catalysis, and doing green catalysis involves using enzymes at industrial scale and cells at industrial scales. Unfortunately, we're not talking about bioreactors and enzyme and microbial growth in bioreactors due to time constraints. But you need to keep in mind that this is a topic that is becoming more and more involved in as a chemical engineer. For example, my research itself has a lot to do with not only protein engineering, but also with metabolic engineering. So engineering cells, cell metabolism for fine chemical production. So there is a lot of that as a chemical engineer that you're involved with, because all these metabolic engineering involves chemical reactions happening inside the cells, hundreds of them at a time, but we are still dealing with rate limiting steps, bottlenecks, substrate inhibition, product inhibition. These are still involved just as much. Okay, on that note, just wanted to mention this to give you some perspective on why we do introduce these enzymatic steps in the class. So yeah, so we're gonna so now we're gonna revisit heterogeneous catalysis with an eye on reaction mechanism. And once again, the things that we're doing here, we're gonna use the rate limiting step for them. The rate limiting step approach. Mostly, there may be a case where one uses steady state approximation, but here we're mostly going to use the rate limiting step approach to determine rate expressions for catalytic reactions on specifically gas phase reactions on the surface of catalyst. Now, I'm going to draw this little nice figure here where if you have compound A is a gas, so compound A as a gas is going to travel. So let's say you have a catalyst where compound A comes in, reacts, and compound B leaves. So the first barrier to catalysis is going to be external diffusion. So to get to, say, this is the first step. So now this is your external diffusion boundary layer, and we'll talk about that in chapter 9 of the book. And then you have internal diffusion. So this is again going to be chapter 9. So external diffusion has to do with, boundary layer where you have flux and diffusivity. Internal diffusion have to do with porosity of your catalyst and diameter of the pores and those kinds of things. So your second step. So A is gonna go in, internal diffusion, external diffusion. Then A is going to get to absorb. So it's gonna absorb on the surface. So this is a third step. This is a surface where the reaction occurs, where A is going to absorb on that surface. That's your third step. And then absorbing on the surface, A is going to react to form B. This is your fourth step. This is a reaction on the surface. Then B is going to desorb from the surface in step 5. B is going to diffuse out from the catalyst in step 6. And B is ultimately going to diffuse out from the boundary layer in step 7. So these are the steps in catalytic reactions. And as a general way, this is what happens. Now, for the lectures and next lecture, we're interested in steps 3, 4, and 5. Okay, and when you get to chapter 9, we'll be interested in steps 1, 2, 6, and 7. So step 3 is adsorption. Four is a surface reaction. And 5 is a desorption. So that's what we're interested in. And you can see, here's what the deal is here. One of those 3 steps can be rate limiting, right? So if you say adsorption is rate limiting, so that is how you derive your reaction rate expression. Surface reaction is rate limiting about 75% of the time in real reactions. So that's often the one that one guesses. If you don't know yet, that's the one you guess to be rate limiting step, because reactions are often slower than adsorption and desorption. So, okay.
Dr. Menard, I have a question.
Yes.
So I'm not sure if it's like more related to chapter 9, but I'm confused what's happening between steps 1 and 2. Like, what is that boundary? Like, what is happening?
Oh, yeah. Okay. Yeah. Let me draw it better. Let me do another drawing here. I'm gonna do this. Oh, actually, let me see if I can call on my art skills a little bit more. All right. Look at that. This is Me and my art skills. All right. So there we go. This is your step 1. I'm gonna do an arrow. This is just step 1, where it goes through a boundary layer. So this is just a boundary layer. And it gets to the catalyst surface. Now it has to travel through there. Say the reaction happens somewhere inside the pores or somewhere at the center. So it's gonna travel there, and this is your step 2. So your step 2 is diffusing inside the catalyst. Does that work?
Yeah, that makes a lot more sense.
Yeah, and then the reaction happens at some surface, and then it goes out another way. Okay. Okay, so yeah, we'll take a moment here, and then now we'll talk about we'll introduce the one topic, which is actually it's not gonna be that foreign to you, because we've already sort of looked at rate limiting step and other things like that. So one topic is called the adsorption isotherm. And when you actually work it out, you find that it goes through the same things we learned. So in some ways, there is not a lot new. So here's, let's do a little graph here. This is a site. Let's do 3 sites. So these are sites of a catalyst. And there is A is gonna come on, and A is going to bind to a site of the catalyst. So A is gonna adsorb. So you're gonna have an occupied site, okay? You also have a vacant site. Now, if a reaction has occurred, A goes to B, for example, B can also be on the surface. So this is in reality what could be happening. If we have a reaction that's ongoing, A gets on the surface, reacts, and then it let's say transforms into B, and B is on the surface, and B is going to leave. So you have occupied states and vacant states. So that's what you end up with. So the reaction here, let's say it's assuming this is a gas phase reaction happening on the catalyst surface. The surface, and let's say A goes to B for simplicity, right? Say it's A goes to B. So that first adsorption step is written as this: A plus S star, right? Now you can see where some of these come from. Gives you AS, and it's a reversible adsorption, so it could leave before it reacts. So you have that step. So that is the adsorption step. And the second thing we know is that our total site concentration is gonna be vacant site plus site that contain AS plus if B also either adsorb or stay on the surface before it desorbs, we also have B as concentration, right? So that looks almost exactly like some of the stuff we did with enzymes. And that's why I wanted to do the enzyme one first. Now, to give you more of a wholesome view, there are 2 types of adsorption. Sometimes I say adsorption instead of, or I say absorption instead of adsorption. Anyway, yeah. So you have molecular adsorption. What does that mean? That means, let's say you have carbon monoxide adsorbs on a catalyst site, and the entire molecule of carbon monoxide absorbed to the site. That's molecular adsorption. Nothing happens to the molecule, it just binds. You can have dissociative adsorption. In this case, and for example, this could happen on a nickel catalyst. I'm just sort of trying to give you more of a wholesome view of catalysis. Now, Professor Hibbett, who's researching in catalysis, could probably do this with his eyes closed and then tell you all about catalysis all the time. But anyway, dissociative adsorption could happen, let's say, on an iron catalyst, where instead you have CS plus OS. So the molecule dissociates and then adsorbs. So you have two types of adsorption. And that's really cool because now, if you remember, you can imagine what we do next, right? So now let's look at molecular adsorption. It's easier to work with. So let's look at molecular adsorption. The other one is also just fine. Molecular adsorption, carbon monoxide goes there and just forms COS. And then we'll just say it's A plus S goes to AS. Just keep it simple. Now the rate of attachment, so we can call it, we'll just call it rate of attachment. We're trying to make this as detailed as possible, but you can sort of guess where it's going. Is Ka times A times S star, right? That's your rate of attachment. Now there's one caveat. That's why we're doing this today. One caveat is in the gas phase, concentration, unless you assume concentration are not easily determined unless you assume ideal gas law, which is not often the case for gases. Some very few gases they only ideal gas law at very low pressures. So often instead of concentration of the gas, we often talk about partial pressure of the gas. So rather than doing this, we often write, and that's the whole reason of why we're doing this, because you often see rate laws written in terms of partial pressures, and they often derive directly in terms of partial pressures because you'd have to get concentrations of the gas, you'd have to assume some kind of gas law. And that's usually not obeyed over the entire concentration range or the temperature or the pressure that you're running your reaction at. So it's often better to do partial pressure. So you can actually write your rate of attachment as Ka partial pressure of A times S star. The only thing that changes here is that now Ka is in inverse atmosphere or inverse pressure. Okay, that's what happens here. So right here, Ka would be in liter per mole per time or something, right? Or liter per mole. Sorry, not per time. Well, yeah, liter per mole per time. Yeah, sorry. But here, you'd have Ka in atmospheres inverse, I guess. Oh, there should be a time involved. Did I make a mistake? Yeah, per time, sorry. Atmosphere per time, inverse, time inverse. So yeah, sorry, make a mistake. Okay. So that is the one change that happens. And the rate of detachment, so the reverse, is then equal to K minus A. So we'll call these Ka, K minus A. So this is the adsorption step, just to keep it consistent. K minus A is just, the rate of detachment is K minus A times AS star, right? Now the overall rate, which call that rate of adsorption, is Ka Pa S star minus K minus A AS star. And you can factor things out. So you have Ka times PAS star minus AS star divided by the adsorption, the equilibrium of the AS formation, which is absorption equilibrium constant. So this is essentially that. So you can now do in the 5 or 6 minutes, we'll be able to finish that particular topic really quickly, but we'll get back to it next class and introduce it again and finish it off. So the you can look at your site balance, right? That's why we did this in the first class. It's because it comes back, right? The site balance, we have our total sites is empty sites plus AS star. For simplicity, let's say assume that only A adsorbs, just for simplicity, because we could have multiple species adsorbing, but we say only A adsorbs. Okay, so if A is the only adsorbing material at equilibrium, see, now we're not talking about rate limiting step. We're just talking about equilibrium of adsorption. That's what we're talking about. Now that step could become the rate limiting step, and we will say next class when that becomes so, we can in fact already solve the rate expression, but we'll do some examples that involve pressure, so it makes it more so you can see the examples involving pressure instead of concentration. But let's say at equilibrium, that rate of adsorption is nearly zero, right? That's, things come in and leave. There's no reaction yet. It's just equilibrium. So you can write that AS star is equal to KA PA S star, and that's equal to KA PA S total star minus AS star. So this is just replacing S star with S total minus AS star. So we've done this similarly with enzymes. And we can plug this, so we can solve for AS star as we had previously solved for enzyme concentration, right? Same idea is Ka Pa S star divided by 1 plus Ka Pa. And if we now divide, so if we take S star, all the terms we don't know, because we don't know AS star, we don't know S star concentrations, we don't know them, but we know things on the right. Or at least we know the pressure because we are the ones. So we know the partial pressures, for example. So this is what is often called the Langmuir isotherm, which is actually it's often it's sometimes simplified as theta A, and this is called the adsorption isotherm. So the Langmuir adsorption isotherm.
I have a quick question.
Yes.
Where did the lowercase Ka go?
Oh, because if you equate RAD to 0, the lowercase Ka is gone.
Oh, right. You can
Yeah.
just divide that out.
Yeah.
And then in your theta term, should it be ST star in the denominator?
Yes, ST star. Yes, of course.
Okay, cool.
Yeah, that's right. So this is essentially the Langmuir adsorption isotherm. The reason I introduce this is because often you'll see, if let's say if you get further into catalysis, they will throw this around a lot, and these will have some significance. Because this is the Langmuir isotherm. There are different other ones. They're names after different people, as you can imagine. Because here we assumed only A adsorbing. We assume that all the sites are the same. So that's another big assumption we made, because we actually didn't even mention that before. We mentioned that all the sites are the same. Often, with some awesome catalysts, you'll find that the sites are different in a way that certain reactants bind, but other reactants bind to other sites. So you can actually have this level of control. And this is often how you achieve selectivity. So it's really cool that way. You can achieve selectivity that way by having sites of different geometry or different affinity for different molecules. But in any case, just kind of give you a general idea. But then you can determine what they call the Langmuir isotherm. And you can plot the Langmuir isotherm as a function of, let's say, partial pressure of A. And this is AS star over ST star. Yeah. And it's going to look, it looks awfully like the Maculus Menta, actually. It's going to look like this. But one thing you would note is that with increasing temperature, the isotherm is going to be uh, going this way with increasing temperature because of the equilibrium lowers with temperature. So you'll have the isotherm will basically change. Let me do a better job here. Let's do a different color because we can. So you have a different color. As you increase temperature, the isotherm will change. So you can kind of look at the temperature dependence of adsorption of a molecule on a surface. There's no reaction involved here yet. Just you can look at how a molecule adsorbs on the surface as a function of temperature. And this is a very important part of catalysis. So this is why the isotherm is important. Okay, we'll stop there because next time what we'll do is we'll start talking about the next step, which is the surface reaction, right? So now we've talked about the isotherm. We did not talk about dissociative adsorption, but you can think about it the same way. If you go through the same process, you'll do the same thing, but you'd get a different expression for it, and you would plot differently. That's really what would happen. But it's the same process, and it's the same process that we introduced a lecture ago. No, I want to reiterate that so that you don't think that this is completely new. This is not new. This is just using this approach that we have developed a lecture ago in systems that are close to, catalysis. This is what catalysis is about. And now, where we're going here is to, or where we're going to by next class is look at the surface reaction and also implement the same process. Look at the desorption, which is pretty much the reverse of that of adsorption. So we will do the same process. In a reaction where there is no accumulation of reactants on the surface, these rates have to be equal. And otherwise, one of them is going to be rate limiting, right? So if the reaction happens and there is no accumulation of product or substrate on the surface, the rate of adsorption, surface reaction, and desorption have to be equal. Otherwise, one of them is going to be rate limiting, and that one is going to be used to determine the rate expression. And the only difference between our rate limiting step usage here and the one that we did with the enzyme is that here it's going to end up being formulated in terms of partial pressures because you're dealing with gas phase reactions on the surface. So yeah, so that's what I wanted to say. And then once we look at all the 3 steps and we do a couple of exercises with if adsorption is rate limiting, what do we see? If surface reaction is rate limiting, what do we see? And there's also some special cases where when you expect, for example, reaction rates to increase with increasing temperature or the reaction rate constant to increase. So there is examples where the reaction rate constant does not increase with temperature, in fact decreases with temperature, and that comes in the rate expression. And the last bet is the temperature dependence of the reaction rate often includes the equilibrium constant. So yeah, so sometimes you will see something like this. If let's say you have a minus RA, as I had it in this could be a K, A. It looks like it is first order. However, the enthalpy of reaction, your delta H, you have 2 terms of energy. You have delta H and you have E, activation energy. So you have 2 terms that determine what your reaction rate constant temperature dependence is. And often you'll find that the enthalpy of reaction is much more sensitive to temperature than the activation energy is sensitive to temperature. as in the E over RT term versus delta H over RT term. So you'll find those to be, to make differences. That some of it is a bit of an advanced move and will not necessarily be, a big, part of your test and whatnot. But I think part of it is to appreciate the complexities of rate expressions. So we'll be doing a couple of examples showing how the reaction rate constant can be, complicated generally. When you see K, it means way more than just K. Yeah, but why this is important finally is that when we go down the line and talk about multiple reactions happening in a reactor, right after we finish the correlation after exam 2, essentially, we will see that the choice of temperature will depend on the activation energy or the enthalpy of reaction. So you will see how that comes into play. So that's why we wanted to make sure you introduce that so you can get an appreciation for it. All right, now the last thing I wanted to say is that I realized that I made a terrible mistake with quiz 4, and I've gotten a couple of emails already about that. So I will make sure that I either, weigh it much less than the other quizzes, or I drop it, depends on, what the scores really look like, because I actually saw that it's a 35% average, and that hurts my soul. So I will do something about it. I realized that the whole quiz was kind of ill-designed. I sort of didn't mean to be kind of a mean person about it. But I will make sure that I make that correction so that you guys don't freak out too much about the next steps. Okay, with that, if there are no questions, we're over time. So if there are no questions, we will stop here. But do make sure that you turn in your homework. If you need more time for the homework, you can always turn it in late. There's no problem, because I do understand that the homework can be a bit challenging. So if some of you have not turned it in and you would like some more time, please do, because some of this homework is important for your exam. So make sure that you have at least tried the homework, okay? Because what I've seen is that fewer and fewer people are turning in the homework, and that does not bode well, assuming that, let's say, second and third exams are not as accessible as the first. So make sure you do the right thing. Okay.